Okay, I think we're going to get started now. The rest of the people can filter in, but our first talk will be by Tim Haines, who's a PhD candidate at the University of Wisconsin-Madison, talking about a generic SIMD library for scientific computing.
Thank you much. All right. As you mentioned, I am a PhD candidate at UW-Madison. I am currently working in the Department of Astronomy, so you might be curious why it is that I'm giving a talk at a computing conference. And that's because my background is actually in computing, and so I've been working a lot on, ChaNGa specifically, which is a Charm product, and interested in n-body solvers and helping to scale them to use accelerators and get better performance on these big machines. Because in astronomy, a big problem is figuring out how the universe works. So we like to be able to solve enormous numbers of particles, measuring into the hundreds of billions and now even into the trillions of particles, to trace the history of how the universe itself formed. So to do that, we employ several different types of n-body solvers. I'm going to be focusing on these tree-based solvers. Some of them also have a particle mesh component, but these are the most popular ones, I would say. There may be a couple in here I didn't remember. But the question is, do they support SPH, or smooth particle hydrodynamics, which is one of the principal ways that we are able to simulate how baryons behave in the universe? Do they have GPU support to make them run faster? And do they have Xeon Phi support? Although the Xeon Phi seems to be phasing out slightly, there are a lot of machines today that exist today and will be here for the next 5 years or so where we would want to possibly run some of these n-body solvers. So if we look way back at Gadget 2, this came out in about 2005, sometime in that range. There is a version called G2X that was developed by an NVIDIA fellow who actually ported Gadget to GPUs, which is why it has GPU support, but it doesn't have any Phi support. Gadget 3 came out a couple years later, has SPH but no accelerator support. Bonsai 1 and 2 is actually a GPU only. Well, Bonsai 1 is GPU only. Bonsai 2 is GPU plus CPU. They found out that if you don't use the CPUs, it doesn't go as fast. But it doesn't have any SPH, so they can't do any baryons. PKD Grav 3 last year ran 1 trillion particles on the Piz Daint machine in Switzerland. So it definitely has GPU support, but it has no SPH support, so it can only do dark matter only simulations. Gothic is another octree solver. It has GPU support, but no SPH and no Phi. Too Hot has SPH and GPUs, but no Phi. Hack is an Argonne Labs product that has SPH, it has GPU support, and it has Xeon Phi support. So this is where we want to bring ChaNGa. We want it to have a yes in this last column right here, and that's what I am working on. Getting, of course, you can compile any program to run on the Xeon Phi, as long as you have a compiler for it, right? But to get good performance on Xeon Phi, you really have to do explicit SIMD optimizations. And as best I can tell, Hack has not done this. If anyone knows differently, please let me know. But soon, ChaNGa will have this. So we want to be competing on the level of software written by a national lab, right? And this is written by a fairly small collaboration of folks at UW-Madison, including Tom Quinn, who was here. And there was a graduate student, Zheng Kuo from Purdue, who was here yesterday. He's also working on this. Okay, so just everyone's probably seen this lots of times. This is the top 500, right? We want to look at compute density. You know, how are things evolving today in the compute landscape? Well, 2 of the top 5 are running on GPUs. 1 of the top 5 is running on a 5. And 2 of the top 5, this PES-ESC and Custom RISC, are running on custom ASIC type systems that are RISC-based, or this is actually a MIPS-based system. So heterogeneity doesn't just mean GPUs. And this is something that I think sometimes folks lose track of sometimes, is that not every machine has a GPU, and not every problem is amenable to being solved on a GPU. So we have lots of heterogeneity out there. And someday, these RISC architectures may actually start being produced with SIMD capabilities, much like the ARM-based architecture and the Neon extensions. All right, so let's look at SIMD support in ChaNGa as it exists today. There are two supported architectures, SSE2, which is from the early 2000s, in both single and double precision. We don't care about integer arithmetic in ChaNGa. Everything is floating point that we need to worry about. It does support AVX, which came out in 2006-ish, but only in double precision. So you can't do AVX with floats in ChaNGa right now. The code to do that is very invasive. There's lots of user-level macros. It's not very pretty. For example, this is sort of a representative line. This is a macro function that you pass in a type and a list of lists, and an index, and oh, this is neat, some sort of business here that gets macro substituted out. Turns out this is actually going to call a constructor and index into an array here and pick out these pieces that you wanted. So this will load 4 either doubles, depending on what this is, or floats, depending on what the underlying, if it's AVX or SSE. So that's not the best. So what do I want to see in a SIMD library? I want it to be single source. That is, I want to write once and use it anywhere. And I'll get more into detail about this in the next slide. I want it to be easy to use because I'm writing for science-oriented folks, not computer science-oriented folks. So I only want the user to specify the precision. Again, we're only dealing with single and double precision stuff here, so we use templates for that. And all the other details, everything else, needs to be handled by the library. I don't want the user to worry about anything else. And we need to specifically cater it to scientific code styles in n-body solvers, which means we do a lot of AOS to SOA conversions. AOS dominates the array of structure format because it's easy to reason about in particle-based solvers. I have a particle. It has a 6-dimensional phase space, 3 positions, 3 velocities, a mass, maybe there's an acceleration in there. And then if I want lots of particles, I just make an array of them, right? And that's the AOS format. It's a nice natural representation. The problem is it has terrible data locality, especially because in most systems, the particle size is actually bigger than 64 bytes, which means that one particle doesn't even fit in a cache line anymore. And the compiler will not auto-vectorize your SOA stuff, so your AOS format. And it permeates the entire code base. So it's very hard to transition from AOS to SOA, as someone yesterday was discussing. So we need something to help us out, and that is explicit SIMD vectorization, which has been attempted in ChaNGa, but is not the best. So what do I mean by single source? Well, it's actually a little bit easier to answer what is not single source. So if your types have an ISA-specific name, like SSE or M256, I don't want to deal with that. I can't deal with that in a generic way. This type right here gets in the way of the user. The user has to know whether or not they're dealing with SSE or float or whatever. I don't want the vector size in the name, because now they need to know if they're dealing with AVX or AVX2 or whatever. So I don't want that in the name either. I want overloaded operators, right? I do not want to have to call SSE add float 4. Blah. And I want to write once and use everywhere. So I want a type that just takes a parameter, and that's it. That's all I want to know is, the user specifies the precision, library handles everything else. Of course, I did not set out to write my own. There are lots and lots of SIMD libraries that exist. Here's just a few of them. The problem is my constraint of single source is not satisfied by the vast majority of them, which including Intel's C++ SIMD classes. This one really blew me away when I found this. It does not support single source. All of the types have both is it an integer, is it a float, is it a double, and is it 8, 16, or 64 bytes, right there in the name. So there's no way to make generic code using that. Dim sum does actually have single source support. This is a prototype implementation for a possible upcoming proposal for the C++ standard to include SIMD support. However, it does not have easy AOS SOA formatting, which is necessary for our stuff, and also doesn't have KNL support. libsymd-pp is in the same boat. BoostSIMD has single source. It has easy SOA AOS. It did have KNL support. It no longer does because a few months ago, the company that owns the code base behind BoostSIMD decided to pull the rug out from under the developers, and so the open source variant of BoostSIMD is now a stripped down version of what it used to be, and we're not sure it's ever actually going to make it into Boost. So we'll see what happens there. I was really sad by this because it satisfied everything I wanted. Right, yeah, so you can pay for the BSIMD version, yeah. And astronomers don't have a lot of money, so. All right, so here's a do-it-yourself SIMD in C++. There are two key ingredients, type traits and tag dispatch, that's it. These are C++ 98 features. Some of these are pre-C++ 98 features. This is old stuff. This is not sophisticated, perfect forwarding and stud tuple and all that fantastic stuff. You do have to sprinkle in a little bit of TMP, template metaprogramming, to fix some edge cases and make sure things compile correctly. At least in my version, because I have converting constructors. So here it is. This is the bare bones of what you need, essentially. So just a template type to take float or double, right? And so we save that away. So this is a little type here. A category comes from a type trait that tells us what kind of SIMD we're using. Are we using AVX, SSE, KNL, all of these things? The SIMD type here is the actual compiler specific type. So _M256 or _M128D, whatever that happens to be. You have a size, which is just the number of elements in your SIMD vector, and a bool type, which is what you need for doing conditionals and things like that. So you just have a type trait that takes that away. So the only piece of data that this class needs to know about is the actual compiler type for the SIMD vector you're using. That's it. And then I just have a representative function down here for overloading the operator plus. What it does is it forwards it off to an add function and passes along the two values that it needs to add together and the category. So this will just pick out whatever category type was returned. And how it does this, or how it figures out which add gets called, is you, at compile time, pick your architecture, right? So you have several of these macros here, the _AVXs, 512s, or the regular AVX, or the SSEs, or whatever. I also have scalar support. I didn't put this on my original list, but it's actually very important for us to have scalar support, that is, not packed instructions, for comparison to current performance and correctness. So it was important to have this as well. This is not offered by most of the other SIMD libraries either. Then I have some compile time controls here for testing purposes, so don't worry about those too much. But this is the only place where macros come into play. This is it. And the only reason we have to use macros is because we need to communicate with the compiler. And you do that through the preprocessor. Maybe in C++23 we'll get some other way of doing that, but this is how you have to do it for now. The user doesn't need to know about any of this. It's all determined at compile time. In fact, which one of these macros here is activated is determined by the compiler flags. So you specify an architecture at compile time, it picks out which set of functions it needs, and away it goes. So if you specify AVX like this, then it'll pull in this header file. And in this header file, we have a bunch of wrapper functions that adds two of these guys and takes a tag. And this is the tag dispatch part. So we had type traits before to determine this guy here, and now we have tag dispatch, and that's it. It turns out, as I was testing this on older versions of GCC, it was very fortunate that I made this decision because The older versions of GCC before, I think 4.8.5 or something like that, did not correctly mangle the SIMD types, and so they could create conflicts in the names here. But the tags here get mangled into the names and differentiate them correctly. So it's sort of a byproduct of the design. So if you had single precision, this one gets called. If you had double precision, this one gets called. And there's no possibility that you could inadvertently convert doubles to floats or floats to doubles because the tags here prevent that. All right, so in a more high-level perspective, the user includes this file. The compiler flag selects your architecture, and then you get a whole subset of these specialized functions that have all been overloaded. And you only get one set of these per compilation unit. This is by design because it's very expensive to switch between SIMD architectures, and there's also a possibility of creating object files that won't run on the specified architecture. That's a whole other talk, but yeah. So we mutually exclusively select these at compile time. It's by design. Okay, so if you were to use the old ChaNGa library, the old ChaNGa SIMD library, and you wanted to implement just one function for the gravity spline, you need this much code. All this does is calculates a spline. That's it. But you have pound if I am SSE, do this. Pound if I am AVX, do this. Here, there are no macros. There is a single template type. Everything is decided at compile time, and the only thing you need to specify is if it's double or single precision, and that's it. This code right here is written once, and it will run on Scalar, SSE, AVX, AVX 512, whatever, PowerPC or whatever it is that we want to do in the future. You don't need to change this at all. Everything gets changed out at compile time. Okay, so let's take a little example. Let's say that you have some particle type and it knows about your three-dimensional position in space. It's not a very useful particle, but there it is. And we want to run a little test. So we make 10 particles, and then we iterate over these 10 particles by just calling the load function, passing in a set of iterators. And it gets back a chunk. And what a chunk is, the SIMD library knows what a chunk is, but thanks to C++11's auto, you don't need to worry about what that is. What you do need to worry about is that you make some SIMD types here, X, Y, Z, these are going to be your positions. So you take the X and you pack into it from the chunk all of the X values that are returned from those particles. So you just pass in a little lambda here and pull the value out that you want. So this takes n different particles, however many particles there are in the chunk. That n is determined at compile time by both the precision and the AVX type. So it could be 4, 8, 16, I don't know. It's determined by the library. I don't have to worry about it here. So there are n particles in this chunk, and then for each particle, I want to pull out its x position and stuff it into a SIMD vector. And then for the y positions, pull those out and stuff it into a SIMD vector, and so on and so forth. So we're taking our array of structure format and we're packing the individual components into SIMD vectors. So this is effectively our AOS to SOA structure conversion here. And then once you've done that, now you can just treat these SIMD types as any arithmetic type, like any other arithmetic type. They have value semantics, they're very simple. All of the operators are overloaded for them, including square root, so that this will actually use on systems that have a single instruction to compute the square root, it will use that. And then you have like the multiplies and adds and all that stuff. And then once you're done doing your SIMD arithmetic, and then you need to take the SIMD vectors and unpack them back into the chunk that you got them from. And you just do it the same way. You take a particle, this time you need a value because you're going to store that out in memory, and you just stick it back into each one of those components. And That's it. So this will work for all of the SIMD types, single and double precision. There is no, the user didn't have to specify any of that stuff. Now the question is, I have 10 particles, right? What if I'm using SSE4 with single precision so that I have 4 floats per pack? Well, I need 3 packs, but one of those packs is going to be half empty. But I didn't tell it that this is a problem. Library figured that out. And in fact, there's a third option to the load function here where you can specify a default value that it will fill in place of actual data returned by these pack functions. The default value is in the pack, not in the load. So out here, you can specify a value for the default. So by default, it's whatever the default initialization of t is, which is usually 0 because we're dealing with floats and doubles. So if you want to make this 1 or something like that, so you don't get like divide by zeros down here, you can specify that as well, but you don't need it. Okay. And if you, so this version is completely generic, right? This is, you could drop this in and never change the way that you could never change, let's say, the header file that the particle is contained in. So you don't need to change the whole code base in order to make this loop run faster, right? If you wanted to, if you have lots of places where you're doing these particle computations, you could take and expand out the pack and unpack functionality into standalone functions, and maybe store those away in the same place you have your particles. And then now we've really cleaned up this loop down here. All of the heavy lifting has been stuck away in these free functions. The only caveat is that now you can use stood tie instead of having to do it one at a time. And in C++ 17, we'll be able to use structured binding to make this one line. And you won't even need to know that there's CK-SIMD of t. You'll just say auto XYZ, pack coordinates, boom, and you're done. And you have XYZ are vector types of whatever the underlying system is that you've configured. Everything else remains the same, and then you just call unpack coordinates. And all the heavy lifting is moved off over here. Oops. Oh, there we go. However, there is a bit of an optimization we can do here. It turns out in ChaNGa, this sort of thing where we have a literal divided by the square root of some quantity is a fairly common operation. And there are several architectures where you can take x divided by the square root of y and turn it into x times the reciprocal square root of y. The caveat here, this is very nice because square root, when you're in, let's say, glibc, is pretty expensive to compute, right? And you're only getting one square root because it's not vectorized. Although in later versions of glibc, they actually do have vectorized versions. But again, the compiler will not auto-vectorize your SOA format unless you happen to be really lucky. So r square root is usually a single instruction, but it usually has terrible accuracy as well. So we need to fix that. And so what we do for single precision is we use a Newton-Raphson iteration to get up to about 1 ULP. The speed up is roughly equal on all the tested architectures compared to the glibc square root plus div. So this is faster for single precision. So executing only one instruction for r square root plus a Newton-Raphson is still cheaper than trying to do a square root iteratively or via table lookup or however they've implemented it. Sincerely doubt it's iteratively, but. And for the double precision side, we use a 5th order polynomial to get about 1.5 ULPs. The speed up, however, is inconsistent. It's about 10% speed up on Skylake, whereas it's about a 3x speed up compared to the square root plus div on Sandy Bridge. So this is uniformly, in single precision, this is uniformly faster, but in double precision, it depends on where you are. There is actually a reciprocal square root benchmark, where I got most of this code actually, that can help you determine whether or not this is going to be any good for you. And of course, you have to test your own software, right? If it turns out the reciprocal square root is not the thing that's taking up most of your time in the kernels, then this is not going to be of much use. but it's there. And how this is implemented is a very simple expression template so that you literally can write this right here and it gets converted into this with the Newton-Raphson or the fifth order polynomial kicks. So there's zero change to the user code and you automatically get these optimizations. Okay, so some future work, forward looking. We need more math functions. Right now we just have square root and reciprocal square root, but we need logs, exponentials, trigonometrics, things like that, and also the error function because we have AVOLD integrations that we do for periodic boundary conditions. It would be nice to also accelerate those. So we need error functions to make that happen. The library does need better algorithms. It needs to make transforms easier to do. So the example I just showed is sort of the basic transform that you can do, but it would be nice to be able to even call stood transform via integration with the STL containers and algorithms with iterator wrappers. This isn't too difficult to do, but making sure that we don't lose any efficiency and we maintain our good code gen along the way. That's the most important piece. We need better AOS SOA conversions. In particular, we need better code gen for pack operations. Currently, you have one load per element that you're packing in, but you also have a branch, and it would be nice to get rid of that branch. So making the code gen better for this is on target. And the BlueGene Q and P backends do not exist right now because I don't have access to any systems like this, but if others do, and I know certainly that ChaNGa has been run on these types of systems before, that would be great if someone wanted to give me some pointers on that, if you've dealt with the SIMD on PowerPC or the new power architecture, I forget what it's called. Open Power, I believe is what it's called. And I have partial implementation of ChaNGa's gravity kernels, but we need to go ahead and fully implement this and then start doing performance and scaling tests to see how things are working, particularly on KNL. This is, after all, the target of all of this, right, is to make us on the same level as Hack. We also can do the SPH kernels. However, they will probably yield less fruit because SPH kernels are usually dominated by the neighbor finding process, and there's not a lot of calculations that go on for SPH. So it'll be determined, this will be done later. We definitely want to get the gravity kernels up and running first. And currently the code is in my private repository. It is not available for public release. It definitely needs a lot of cleanup. Too much hacking has gone on. There's not enough structure in the code right now. But it does work. So it definitely needs cleaned up, and then I want to release it for the public because, as you saw in that list of 10 or 12 SIMD libraries that I had there, none of them had everything I wanted. Boost SIMD was the closest, and it was going to go into the Boost library, which is the #1 C++ library outside of the STL. So yeah, that is all I had.
I have a few. Did you look at Blaze or Eigen, since everything you've shown has been implemented already? Like, this is nothing new.
Right. No, it's nothing new.
So
yeah. Blaze and Eigen are more linear algebra based.
No, they do this. We do this with them. Exactly what you just showed.
Right. You can. Yes. You can do this with GrowMax, except that it doesn't have single source. But Blaze and Eigen, I didn't check to see. Do they support single source?
Yes.
Oh, fantastic. Okay.
They do everything that you do here. Is you just, it's a header only library. You just link it in. And
okay.
So it might be consider switching if that's an option, because the only thing you would have to do is write your pack and unpack. It supports. I think the only standard math functions that Blaze currently doesn't support is xm1 and log p1.
Okay, sure.
But other than that, it does all of them. It supports everything from old SSE to KNL. It also doesn't have the BlueGene Q and ARM.
Yeah, none of them do. So yeah, I don't know if that's an IBM thing or something, but yeah.
Yeah, my guess is so this application is developed in Europe. So if there aren't many Blue Gene queues in Germany,
that's
then
probably
maybe,
true.
I don't know.
Yeah.
So yeah, that's maybe might save you some time going forward.
Okay, sure.
So and they use the Intel SVML. So I don't know if you're aware of that.
Okay.
So they kind of can cheat to get extra vector instructions that maybe
Yeah.
don't exist at the hardware level. But yeah.
So can you elaborate on that conditional in the SOA, the packing business? The last slide you mentioned the conditional that remains there.
Yeah, you know what, honestly, it's probably easier if I actually just show you the code.
Or maybe, should I just do it offline?
Maybe I'll show you the code offline, but it's just a for loop that checks. There's a static number of trips, but it doesn't know whether or not the nth element is in the iterator's range. So, yeah, it has to check. It has to check. So doing this better is not the next thing to do.
Is there support for like fused instructions or?
Oh, yes, I forgot to mention that. Yeah, so if you compile with AVX2, this is the super architecture under which FMA does fall. And so if you compile with AVX2 and you have an FMA capable compiler, it automatically converts them to FMA. At least in the compilers that I've tried, which are GCC, Clang, and Intel.
Thanks.
Yep.
Let's thank the speaker.